In this video, we'll be diving into the world of graph traversals. We will be covering two fundamental algorithms: breadth-first search, often called BFS, and depth-first search, known as DFS. These algorithms are essential for exploring and analyzing graphs, and understanding them is a key skill for any computer scientist. Before we delve into graph traversals, let's define what exactly a graph is. A graph is a nonlinear data structure composed of nodes, also known as vertices, and edges that connect these nodes. Vertices are the fundamental units of a graph, and edges are the links that connect pairs of vertices. Graphs can be directed, meaning the edges have a specific direction, or undirected, where the edges have no specific direction. They can also be weighted, where each edge has a cost or value associated with it, or unweighted, where all edges are treated equally. Now let's discuss how graphs are represented in computer programs. The two most common methods are adjacency lists and adjacency matrices. An adjacency list uses a dictionary, or a similar data structure, where each key represents a vertex, and the corresponding value is a list of its adjacent vertices. An adjacency matrix, on the other hand, is a two-dimensional array where each element indicates whether there is an edge between two vertices. If there is an edge between vertex I and vertex j, the element at matrix ij is 1. Otherwise, it is 0. So, what exactly is graph traversal? Graph traversal is the process of systematically visiting, checking, and/or updating each vertex in a graph exactly once. The order in which these vertices are visited defines the traversal strategy. Graph traversal has many real-world applications, including pathfinding algorithms like GPS navigation, web crawlers used by search engines, social network analysis to understand relationships between people, and even solving puzzles and mazes. Let's start with breadth-first search, or BFS. BFS explores a graph by visiting all the neighbors at the current depth level, before moving on to nodes at the next depth level. This means it visits nodes in order of their increasing distance from the source or starting node. BFS is particularly useful for finding the shortest paths in unweighted graphs, because it explores all possible paths of length 1, then all possible paths of length 2, and so on. BFS is a complete algorithm, which means it is guaranteed to find a solution if one exists. BFS uses a queue data structure which follows the first-in, first-out principle. Here is how breadth-first search can be implemented in Python. First, import the deque object from collections. Define a function called BFS, which accepts a graph and a starting node as arguments. Initialize a visited set with the starting node to keep track of which nodes have been explored. Also, initialize a queue with the starting node. Initialize an empty list to store the order in which the vertices are visited. While the queue is not empty, dequeue a vertex from the queue and add it to the result list. Then iterate through all of the neighbors of that vertex. If a neighbor has not been visited, then add it to the visited set and enqueue it. Finally, return the result list. Now let's discuss depth-first search, or DFS. DFS explores a graph by going as deep as possible along each branch before backtracking. This means it explores one branch completely before exploring other branches. DFS has various applications, including topological sorting, detecting cycles in a graph, and maze generation. DFS can be more memory efficient than BFS for certain problems, because it does not need to store all of the nodes at a particular depth level in memory. DFS uses a stack data structure which follows the last-in, first-out principle. It can also be implemented recursively, which uses the call stack implicitly. Here is how depth-first search can be implemented in Python. Define a function called DFS, which accepts a graph and a starting node as arguments. Initialize a visited set and a result list. Then define a recursive function called DFS_recursive, which accepts a vertex as an argument. In this function, first mark the vertex as visited and add it to the result list. Then iterate through all of the neighbors of that vertex. If a neighbor has not been visited, Then call the DFS underscore recursive function on that neighbor. Call the DFS underscore recursive function with the starting vertex as the argument. Finally, return the result list. Now let's compare breadth-first search and depth-first search. BFS visits all the neighbors at the current depth before moving deeper, while DFS explores as far as possible along each branch before backtracking. BFS uses a queue data structure which follows the first-in, first-out principle, while DFS uses a stack, or can be implemented recursively. Both BFS and DFS have a time and space complexity of O of V plus E, where V is the number of vertices and E is the number of edges. BFS is best used for finding the shortest path in unweighted graphs, level-order traversal, and finding connected components. DFS is best used for topological sorting, cycle detection, and maze generation and solving. In conclusion, let's look at some real-world applications of graph traversals. These include finding connections between users and friend recommendations on social networks, indexing pages by following links between websites for web crawling, finding the shortest routes between locations for GPS navigation, and decision trees and maze generation in game AI. BFS uses a queue and explores level by level, while DFS uses a stack or recursion and explores depth first. Both have a time complexity of big O of V plus E. The choice of algorithm depends on the problem characteristics. The choice between BFS and DFS depends on the nature of the problem you're trying to solve. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.